Right, good afternoon, everyone. And thank you, Ken, for the nice introduction there. Calling a little bit of an audible here, so I got the heart rate going a little bit to fill in, but happy to be here. I am Brian Wawczak from the Metropolitan Water Reclamation District of Greater Chicago, also known as MWRD or MWRD-GC. It is a mouthful. We generally just say the district back at the office, and I'll probably revert back to that just out of habit during the presentation, so forgive me ahead of time. But it's always an honor to talk about one of our many excellent and diverse projects, and the Tunnel and Reservoir Plan is no exception, also known as TARP, or Deep Tunnel, some people call it. It is one of the exceptional and excellent projects of the 20th century, and now moving into the 21st century. It's a project that's been emulated not only in the United States in different cities, but actually all over the world, in London, in Singapore, in Japan. It is our region's solution to flooding prevention and pollution control. And it seems to be working wonderfully so far. I can say that it's very appropriate and special to talk about it this year because it's the 50th anniversary of TARP. It was originally adopted by our Board of Commissioners in 1972, same year as the Clean Water Act was enacted. So certainly a very monumental year in the water environment sector. So what is TARP? It's a system of very deep tunnels and vast reservoirs that collect our combined sewer overflows, what we call CSOs, before they can make their way to the waterways and pollute our water and Lake Michigan. So before I dive into TARP, and I say that figuratively, of course, I don't want to literally dive into TARP, but I thought it would be good to talk a little bit about the mission of the district and how TARP complements that or supplements that. So the district, or MWRD, was formed, in 1889. Our initial major project was the reversal of the Chicago River, which is an entirely different presentation. I could probably talk 60 minutes about that, but we'll save that maybe for next year if Ken invites us back. But our main mission now is to manage and treat wastewater. We do that for the city of Chicago and 128 different suburban municipalities. Our service area generally covers Cook County minus a couple of different pockets. It's 883 square miles in size. We serve 5.25 million people. And then when you include commercial and industrial flows, the population equivalent actually jumps up to 12.75 million. So we're serving quite a big core populace. We also maintain 560 miles of interceptor sewers. So what those interceptors do is they essentially collect every local sewer system and take those flows from each suburban municipality in the city of Chicago and then transport those to our treatment plants for treatment and processing. We have 7 treatment plants, including Stickney, which Commissioner Perry mentioned earlier. Stickney, the largest treatment plant in the world. We treat 750 million gallons of flow on average per day. You can see this is located southwest of the city of Chicago. You can see the skyline here in the background. We have 6 other plants as well, so 7 total. And we actually don't call them treatment plants anymore. They're reclamation plants because one of our other core mission points is to reclaim resources. We reclaim phosphorus and other nutrients, algae, biogas, which can be converted to electricity, and that helps us towards our energy neutrality goals, biosolids, which can be processed and become fertilizer for commercial and residential applications. So we're doing a lot at the plants. One of our other core missions is to manage stormwater. We've been doing that since 2004. So TARP supplements that because we can accept overbank floodwaters and store those so that floodwater is not making its way to our basements, into our homes. We also are custodians of the local waterways. We protect the local waterways in terms of water quality, making sure that it meets NPDES standards. TARP helps with that by capturing these CSOs, these combined sewer overflows, so that pollutant sewage can't make its way to the waterways. And then finally, maybe most importantly, we protect our region's most vital resource, and that's Lake Michigan, the fresh, clean, natural drinking water found in the lake. Lake Michigan on its own serves 40 million people with drinking water. The Great Lakes, one of the largest freshwater surface ecosystems on planet Earth. So certainly vital and important to continue doing that. TARP helps out by that, doing that by reducing river backflows. And then the other bullet points here, we eliminate CSOs towards the waterways. We provide, bear with me here as I can't read that, an outlet for floodwaters so that the floodwaters, as I mentioned, don't make it to our basements. We try to comply with federal and state laws, the NPDES standards I mentioned, and then we try to accomplish this in the most cost-effective manner. So the next 4 slides are really, I love these are really excellent. It's sort of an illustration of the before and the after with TARP. So prior to 1972, the local sewer systems would essentially capture all of our residential and commercial sewage flows and then transport those to our district interceptors. And again, those district interceptors would take the flow and transport it to our treatment plants for treatment and processing. That worked great in dry weather conditions. However, as we saw in the 1950s and the 1960s and the baby boom and post-baby boom era with continued development in the city of Chicago, in the inner ring suburbs, in moderate to heavy rainfall conditions, the hydraulic loading on our local sewer systems became so great that the sewage had nowhere to go. It couldn't make its way into the interceptors or to our plants, so it outletted to the local waterways, essentially CSOs, and this became more and more of a prevalent problem. So in 1972, the district came up with this plan called TARP, and it was broken into 2 phases. Phase 1 would be the construction of very large tunnels, very deep. Those tunnels would essentially capture diverted flow from the local sewer systems prior to outletting to the area waterways. And we would store that flow in the TARP tunnels until the storm passed. Once there was capacity at the treatment plants, we would pump it up and then treat it and process it before outletting to our local riverways. But that wasn't all. We also had another phase coming up, and that's phase 2. If I can get the slide to, there we go. And this is a great slide. This is excellent because it shows some context to how deep the tunnels are and how vast the reservoirs are. So we added 3 very large reservoirs. In the upper right corner, you can see how shallow the local sewer system is in our district interceptor in comparison to the tunnels and the reservoirs. So we were able to increase our total storage here by about 10-fold with the addition of the reservoirs to the TARP system. So again, it's working great. Just a quick timeline of what's been done, and it really starts before 1972. The district and the Army Corps of Engineers had a lot of conversations, and there were various plans that were discussed, different TARP systems. But the final plan that was agreed upon was adopted by our board in 1972. Took a few years to get the design plans going. So construction began in 1975. The first tunnels went online in 1985. Tunnel construction was essentially completed in 2006, minus a couple of connecting tunnels on the smaller end. And then just going backwards, our first reservoir came online in 1998. That was the Majewski Reservoir. 2015, our largest reservoir, the Thornton Composite Reservoir, came online. That was Thanksgiving weekend 2015. And then the final piece of the TARP puzzle, the McCook Reservoir, stage 1 came online at the end of 2017. And then stage 2 will be completed, if all goes well, in 2029. So this is a map of the TARP system. The green and the blue lines are the mainstream and the Des Plaines tunnel systems. Those are respectively 41 and I believe 27 miles in length. Those are tributary to the McCook Reservoir just southwest of the city. The upper Des Plaines tunnel system is 7 miles in length. That's tributary to the Majewski Reservoir. That serves our northwest suburbs. And then the Calumet tunnel system, shown on the bottom of the screen, that serves our southern suburbs and the city of Chicago south of 79th Street. and that system is 36 miles in length. That's tributary to our Thornton Composite Reservoir. So when it's all said and done, all of the tunnel runs and the 3 reservoirs will hold 20.5 billion gallons of storage. What's been built to date? So far we have 109 miles, just over 109 miles of deep underground tunnel. Most of it is 30 to 33 feet in diameter. 264 drop shafts, up to 25 feet in diameter. 19 construction shafts, 3 major pumping stations which take that flow and pump it up to our treatment plants for processing from the TARP tunnels and the reservoirs. And then over 600 surface connecting or regulating structures. So how does it work? This is a plan view and then below a section view. So as our local sewers fill up in heavy rainfall events, that water can't be processed at the plants, so it starts to back up towards those old outfall locations along the riverways. But before it can get there, we have what we call now connecting structures, which sort of intercept the sewers, and the CSO waters will drop into the connecting structures. They're diverted to a regulating structure, which has a sluice gate, which is either operated manually or automatically. And then from the sluice gate, the CSO water drops down a drop shaft, I guess it's aptly named, right? A drop shaft, then into our TARP tunnel. So interesting note, the drop shafts actually have 2 different chambers. One chamber to accept those incoming CSO flows. The other chamber allows for the displaced air from the tunnel system to rise back up to the surface to escape through an open grate. And this is what we're trying to prevent. It's an old photo. This is a CSO in action. This was along the Des Plaines River, I believe, in the late 1990s. Well, we don't see many of these anymore. These have been virtually eliminated in the Calumet service area. They have been eliminated in the upper Des Plaines area. We do see some still happening in our mainstream area, in the tunnel areas that are tributary to McCook. We're anticipating with McCook Phase 2 coming online later this decade that we will drastically even reduce these CSOs that are happening along the Chicago River and the Des Plaines River. Here's a photo of the construction of the tunnels sort of in action. This is a location just north of the McCook Reservoir where 2 tunnels connect. We have very large boring machines that go through the bedrock. And before we place the tunnels in operation, we line them with a 12 to 18 inch thick reinforced high strength type RA concrete tunnel liner. Majewski Reservoir. This is the reservoir just outside of O'Hare Airport. I think in this photo, in fact, you can see O'Hare, and then in the very faint background, the Chicago skyline. This is the smallest of our reservoirs. It only holds 350 million gallons of water in sewage. Again, this came online in 1998. It's named after one of our commissioners from the 1980s and 1990s. The Thornton Composite Reservoir, this is one of my projects, completed in 2015. This is a view looking east. I-80, I-294 is on the right side of the screen. The largest CSO reservoir of its kind in the world. It is a half-mile long, a third of a mile wide, 297 feet deep, holds 7.9 billion gallons of CSO water, and we also are able to accept Thorn Creek overbank floodwaters. So it's a combination CSO and floodwater reservoir. If you were to fill it up with 55-gallon rain barrels from top to bottom, north to south, east to west, and then take those rain barrels out and line them up front to back, end to end, the rain barrels would circle the earth 3.5 times. So I triple checked that calculation, and it's just double check me on that, but it's amazing. So it was mined out by Hanson Material Service. It's the north lobe of the Hanson Material Service quarry, which the district now owns. We created a grout curtain around the perimeter to make sure that the aquifer around the reservoir was protected, and also to keep the CSO water inside the reservoir, and that seems to be working tremendously as well. We have groundwater monitoring wells around the reservoir that we check on a quarterly basis. So everything's working great, knock on glass, but very proud of this project. Another photo from inside the reservoir. This is at the water service. We maintain a 20-foot maintenance pool in the reservoir. And on top of that maintenance pool, we have 20 solar bee aerating units that create a 5-foot deep oxidized layer beneath the surface to keep any odors sort of below that surface so they don't permeate up into the atmosphere. In the background, you can see the 30-foot diameter TARP connecting tunnel that goes to the Calumet system. And finally, the McCook Reservoir. So stage 1 went online in 2017. That holds 3.5 billion gallons of water. Stage 2, the last component, as I mentioned, will be coming online in 2029. That'll bump us up to a total of 10 billion gallons, so adding another 6.5 billion gallons. So this photo is looking southeast, if my bearing is correct here. I believe that's the I&M Canal on the left, the Stevenson Expressway on the right, and then the Des Plaines River just right of that. McCook Reservoir, I should mention, was mined out by Vulcan Material Service, similar to Hansen Material Service, HMS, in the Thornton area. So, of course, any great project has challenges. So I thought we would talk about 2 or 3 of those right now to be transparent and talk about some of our solutions. One challenge is odors. We're talking about sewage and solids, which can collect at the bottom of the tunnels over time, especially if there's a big difference between rainfall intervals. And with solids, you have hydrogen sulfide buildup, H2S buildup, and then when there is a storm and then there's sort of a flush, that H2S gas gets pushed up towards the surface and usually, in some cases, I should say, escapes through a drop shaft. So most of our drop shafts, and we're looking at a photo here of a drop shaft on Canal Street in downtown Chicago. Most of our shafts are located in forest preserve areas, industrial areas, away from our business districts and residential areas. But there's a possibility that odors can come up. So what have we done to overcome this challenge? So the district can utilize, when this happens, and it doesn't happen at every drop shaft, we have a louver system we can install. We have shaft covers. We've actually been working on a proprietary odor control vapor misting system in one location that seems to be working wonderfully. It doesn't just mask the odors, but it actually neutralizes the odors. Another issue, transient flows. And I have to admit, this is a little bit even above my understanding. We have hydraulic modelers at the district that look at this all the time. But what can happen because of the invariability in rainfall events, and of course our service area and the TARP system is so vast in size, the downstream end of a tunnel can fill very quickly. The upstream end can be filling very quickly at the same time. And what we see is water is trapped sort of in between. Not water, air is trapped in between, and the air has nowhere to go. It tries to escape as the downstream flows are pushed into the tunnel towards the downstream end. The air is trying to escape. It's trying to bubble out, taking the path of least resistance. So we can see some bubbling, and sometimes we can see even geysers of some sort. So these 2 examples are photos from the Chicago area. The most famous example, if you go to YouTube and type in Minneapolis 1999, there was a very large geyser that happened on a highway. It blew off a shaft cover that was like 20 feet in diameter, and luckily nobody was killed, but certainly a very dangerous situation. So how do we remedy this? So we can implement air relief valves, trade out manhole covers for grates, and try to allow some sort of air relief happening in the modeled areas where we see this happening on more than one occasion. And finally, maybe most importantly, just kind of talking like as an overview on TARP, we're very happy with the TARP system. It has taken quite a bit of time to implement, 50 years to this point. Its cost in today's dollars, $1.8 billion, taking into account inflation to build. So we realize moving forward, gray infrastructure, tunnels and reservoirs are not necessarily always going to be the answer. So we're trying to come up with ways to supplement those. And one idea is green infrastructure. And it allows us to look at flooding on a very hyper-local or hyper-regional level. And one other just kind of quick add-on, we're noticing with climate change and some of the storm events we're seeing now that are higher intensity, but maybe smaller duration, but it just happens very quickly. Our local sewer systems are completely inundated very quickly. The hydraulic loading happens and they're at capacity. There's nowhere for the water to go, even if our TARP system is still dry. We've still got room, we still have capacity, but the local systems are sort of like a pinch point and they can't get the water to TARP. So green infrastructure is an idea, and I'm going to show you very quickly two examples. One is the idea of curb bump outs, where we have sort of a engineered soil stratum where water can be directed from the street through a curb notch into this soil stratum with native vegetative plantings, and it will gradually seep into the ground, either further down into the surface or into an underdrain where it then can be directed back into the local sewer. But timing-wise, we'll give the local sewers a chance to empty out, and then this water can come in when there's capacity. And there's lots of benefits to this. Aesthetically, if it's maintained, it looks great. There's an educational value. There's a safety value with traffic calming, a smaller pedestrian walkway to cross a street. So this is one idea, again, on a very hyper-local level. Another idea is permeable pavers, and these require maintenance as well, but you have these openings in a paver system in a parking lot or in a street. It allows water to drain down into a stone stratum where the water can be held, and then either eventually draining down lower into the soil or into an underdrain and then back into the local sewer system. But again, it's sort of a delay on getting that water into the local sewers immediately. So something to consider in the future. So we're very happy with TARP. It's an amazing project. We've seen so many benefits so far. As I mentioned, the CSOs in the Calumet and the Upper Des Plaines area have been eliminated. With McCook coming online, we're seeing that CSO, with McCook Phase 1, our CSOs captured went up from 28% to 70%, and we're hoping with Phase 2 that it goes up even higher. The water quality has improved in our Chicago area waterways, what we call the CAWS, another one of those government acronyms we keep talking about. Dissolved oxygen levels are much higher. The bad stuff is much lower, suspended solids, ammonium is nitrate, cyanides. Fish species has increased. From the 1970s, we had 7 documented species. Now we have 76. Recreational opportunities are afloat. No pun intended there. And then the picture here from the Michigan Avenue Bridge of downtown Chicago. If you're in town for the first time, if you have a chance to check out the Riverwalk on the south side of the river from Lake Street on the west end all the way to Michigan Avenue on the east end, it's amazing. It's one of the city's jewels. The photo, the kind of the view of the skyline from there is really just an incredible thing. So check that out. But we're happy with TARP. And then moving forward into the future, we see benefits happening as well. So thank you. Appreciate your attentiveness, and hopefully that lived up to your expectations. There have been a lot of really great panels and speakers so far today, so appreciate your time. Thank you.